Hi everyone, in this lab we are going to measure the vibration of a cantilever beam using a strain gauge. So the goal here is to compare the experimental and theoretical results of the vibrations by measuring the natural frequency and the damping ratio of these cantilever beams. So like what we did last time, we have a beam and we have some sort of fixture for making a cantilever beam, and we have a strain gauge attached near its root. And in lab 7 we measure the displacement, the deflection at the tip, right? On the other hand, in this lab it's going to be slightly modified. So in this case we are going to attach the beam with a strain gauge at your workbench. This should be your table, and you're going to use a C-clamp to hold the beam sitting on the table, okay? And the rest is going to be similar. So your strain gauge as being a component of this Wheatstone bridge, you're applying plus and minus 5 volt DC, and that should be grounded. And the other side is going to be used to measure your output voltage, and you are applying some gain, and this is the amplified output, and that is going to be connected to the PC, okay? So when we do this experiment, we're gonna basically ding this cantilever beam, so it's gonna boing, oscillate, and then it eventually will die out. And we're gonna do this with two different cases without any tip mass, just a raw beam like this. And you also have to do this with adding a tip mass. Probably it's going to be 50 gram, or depending on the mass you pick, you're going to add a 100 gram mass, and that kind of looks like this. And you're going to add that at the tip, and you just repeat the experiment. Just sting this and let it bounce, move back and forth, and then it dies out. So without the mass, your response curve may look like this black line, and with the mass it may follow something like the red line we have. So what we see here is the black one without the mass, it oscillates faster, and the one with the mass, it oscillates slower like that, okay? And that is analyzed by measuring the natural frequency. So with the mass, our natural frequency is going to get lower, and this is the equation for the natural frequency. So natural frequency in radian per second, omega n, is square root of the effective stiffness over the effective mass. So like I said before, we are going to compare the experimental and theoretical results. So in the experiment, what you're basically going to do is you're going to measure this time response using the NI DAC, and that is going to be stored in your PC. And from here, you want to find the natural frequency, okay? So we're going to have some value, the natural frequency, right? And that should be same as the theoretical result, which is K over M, the effective stiffness over the effective mass, and your effective stiffness is going to be approximately 3 times E, the Young's modulus, I, divided by L cubed. And after using this, your effective mass is going to be approximately 0.2357 times mass of your beam. So total mass of the beam times this is going to be approximately your effective stiffness. And if you're adding something at the tip, your effective stiffness is going to be 0.2-ish times of your mass of the beam plus the mass at the tip. So it's going to be this times 0.2357 plus the mass of this guy, okay? So we can see that from this equation, as we add more mass, as the mass gets larger, the natural frequency gets smaller. The small natural frequency means it oscillates slowly. So compared to the black line, which is without any mass, the red line is oscillating slowly like that, okay? And a couple things that we would like to note is that, like the previous lab, we need to check whether the strain gauge is functional by monitoring the strain resistance changes. So you have that beam and strain gauge applied, and you just bend this thing slightly, and the resistance value is going to slightly change. So we need to make sure whether your strain gauge is live or dead. That's the first thing we want to do. And then when you clamp this beam on your workbench, make sure that the strain gauge is not sitting on top of your table. You would like to have something like this. Your strain gauge is close to the base, but it is outside of it. That way, when this beam is being bent like this part is the part that has max strain, so you can measure most out of it. If your strain gauge is sitting on top of the table, basically this part is like fixed, right? So it's not going to be bending or doing anything. So you might get something that is tiny because the strain is very small here. Okay, so not on the workbench. You should have something sticking out like that. Okay, and also you are required to measure the dimensions of the beam. By the way, the thickness is about an 1/8 inch, and the width is about 1 inch, and this is an aluminum beam. So for some deliverables, you may need to find the Young's modulus of the aluminum beam from Google, and also you need to know the length of the beam. So when you measure it, you want to measure it from here to there, not the total length of the beam. You see what I'm saying? So it should be from here, from the edge where you clamp to the tip of the beam. So that is going to be the length that you want to measure, not the total length of the beam, not this one. Okay, all right, so I'll see you guys in the lab.